Okay, this is good. I think record is on. Should be. All right. So the story starts from a network. So let me first draw the network. Then from there we can basically refer to that network over and over. So you may draw it somewhere else because I'm going to scroll it down and up. You may have it in front of yourself also because we're going to keep basically looking to that network. And since I'm writing from my notes, it's going to be sometimes hard for me to scroll up and down. So if you have it in front of you, it's going to be easier. So consider this network. So I have two input. Let me call this input, you can call it X. Let me call this unit I1, and let me call this unit I2. And then I'm going to have two hidden units. Let me call this one H1. Well, let me draw it differently this time. I'm going to make it a little bit larger. I have a reason for that. I'm going to put its name outside of it, H1 and H2. I'm going to put a line here. I have a reason for that, and now I'm going to explain it. And I'm going to put two output network. To output also, I'm going to treat it exactly the same as hidden layer. So I'm going to draw a larger circle for that. Oops. My circles are not quite circle, but that's fine. Since I'm not looking at the monitor right now, if you have any question, please feel free to talk because sometimes I may lose your note here because I'm looking at my iPad right now. So if you have any question, if you need explanation and you need to stop me, feel free to let me know, okay? Just whenever you like. So this is O1, this is O2. Output 1, output 2, okay? So we're going to set up our network like this. So in order to make it probably, yeah, let's put it this way. So I'm going to put it here, this guy, and this guy. Maybe I can use a different color for that. Here, here, right? I'm going to have one blue here, one blue there, and maybe green here and here. Yeah, my network is amazing, right? Let me call wait, since right now you understood those V and W's, I'm going to call it W, all of them, but I'm going to give it a proper index. I'm not going to use the indexing that I showed you in the lecture notes just for the simplicity. So let me call this one W1. W1. Let me call this guy here W3. And let me call this one W2. And I'm going to call this one W4. Good. And likewise, I'm going to call this one W5. I'm going to call this one W6. I'm going to call, sorry, maybe I can do this one. This one W7. I'm going to call this one W6. And I'm going to call this one W8. I'm going to add two more nodes here. One node here, one node here. These are my bias. So bias always has the content of 1, as you see here. Let me right now I'm going to use this funky black white. One there, one there. one here, and one here. And their corresponding values, it's going to be similar. I'm going to call both of them B1. So these two, let me call this one B1, small b1. I want to call this one a small b1. Oh, this is ugly. I'm going to call this one a small b2 and a small b2. Good. And of course, I have the I have the output here, and I have another output here. Good. So far, any question? Now it comes to the values, right? So let's say the initialization of the W's, I'm going to just put right next to them. Or maybe I can just make a table or something. Let me put it here. So basically, I want to make it like this. Let's make a table. So 2, 2, 4. How many weights I have? 2, 2, 4, and 2, 2, 4, 8, 9. Totally 9. So, okay, let me draw this. I might need to extend that, but that's okay. Here is W1, W2, W3, W4, W5, W6, W7, W8, and 9. We don't have 9, right? Why did I put 9? A B, right? I think it's B1 and B2. B1 and B2. All right, quickly, I want to put that. Actually, I have 2 more values here. I'm going to put it here. I1, for example, and I2, these are for inputs, right? These inputs here. I'm going to put all those inputs. So for example, I'm going to start working with the data points of this. So I1, I'm going to call it 0.5 here. I2 is 1. So these are given to me, okay? So this is not something that, so W1, let me call it 0.15. W2, let's call it 0.2 or 20. W3, yeah, W3, let's call it 0.25. W4, let's call it 0.30. Let me just double check it here. W4 is here, and W3 and W2. W2, okay, sounds good. So W5, I'm going to call it 0.4. W6, 0.45. W7 is 0.5. W8 is 0.55. And B1, B2 is 0.35 and 0.60 or 0.6. All right, so consider this W's as initialization, and I1 and I2 are 2 data points, and from my table that I just gave it to that. Now, the output of this is that my desired output here is point. I mean, it could be anything, right? I'm going to write it here, actually. The O1, I had to kind of continue this table, but I don't have room here. So let me call this O1 here. O1, it's equal to 0.01, and O2, this is the output, okay? O1 and O2. So basically referring to this one. O1 and O2, it's equal to 0.99. So that output, if you see here, so for example, if you consider that as a binary, so basically this one I say 0.99, this is 0.01. You can consider it, for example, O2 is 1, and this is almost 0. right? Something like that. You remember we talked about all those, how we are going to basically define the output and how we can basically use that for the classification. So right now, the training output is, the output for that is 0.1 and 0.99. Let's first look into the forward forward path. So this is something, for example, we got it in our table, right? Now, with this given weights, first I'm going to demonstrate a forward path. A forward path from beginning to the end. I would like to see what my network would return with this given data, right? And I would like to compare the output that my network will generate with this given data to the output that I desire to have, right? If I have that difference of the error, then I can use my back propagation to update hopefully my weight such that I get a closer result to this. Does it make sense? Does it make sense? Yes, no, sometimes, not today.
Yeah.
All right. All right, so I'm going to start. I'm going to call this section. I hope you guys drew these things in front of you. I'm going to back and forth going up and down, but I know it's going to be annoying on the monitor, but I'm going to do that. But it would be beneficial if you draw it yourself as well. If you need time to do that, I can give it a time. So you can just gonna go through that. If you need more time, let me know. If I'm fast, let me know. Or even if what you can do, you can just listen because I already have this one. I'm going to upload this. So that also is not a bad strategy either way. So please pay attention to kind of learn that. So the first step I'm going to call the forward pass. Feed forward, it's better to say, or feed forward. Okay. So the first step here is to calculate the net of H1 and the net of H2. Once you have net of H1, then you're going to pass it to an activation function. Activation function, by the way, here I'm going to use as sigmoid, or sometimes they call it logistics or sigmoid. So that's why I kind of divide H here. So this one, oops, this part basically calculate the summation. Let me call it net. And this part, basically, it's activation. Okay? I just put it here, so all of them. So here also is net. Actually, let me write it this way. Net, activation. Net, act. Net, act. Okay? All right, let's start from net of H1. Net of H1 is I1 multiplied by W1 plus W2 multiplied by I2 plus the bias. Make sense? So let's do that. Net of H1, it's equal to W1 I1 plus W2 I2 plus B2 multiplied by 1. Why 1 here? Because the value of that is always 1, right? And it's why B2, B1? Before you guys complain, B1. Now, if I plug the numbers here, this is equal to 0.15 multiplied by 0.5 plus, if you have numbers in front of you, you can just keep checking as well. This is my calculation, and always prone to error. I try 35 by 1. This one should give us something like 0.3775. Make sense? All right. So if I got back up here, I'm going to put some time here. You guys can write it if you're writing. Are we good?
Yes.
All right. Now, if you look into that, so we calculated this part. Now I have to pass this net to an activation function, right? Which is sigmoid function. Sigmoid function, it's given by this. I think this is a general sigmoid. F of x, for example, it's equal to 1 divided by 1 plus e to the negative x. This is a general sigmoid function. Now I have to, instead of this x, I have to pass net of h1. So basically, I should say, I'm going to call that out here. So basically, the output of this, previously I called it y. You can call it y as well, but I try to call it what unit is that. So later on, when you look into that, you can understand that. So I can call it out of h1, right? So out of h1 here, it's equal to 1 divided by 1 plus e of negative net of h1, which is equal to, I'm going to write it explicitly for a few of those steps, then later on I'm going to go faster so you can kind of understand the whole process. E plus negative 0.3775, which is almost equal to 0.5932 69992. Maybe you don't have to go that big. You can just stop in 4 digits maybe, or even 2 digits after. Good. So in our lecture, we call that y1, for example. This is the same. Good. Question? Now, I want to do exactly the same for, see, look at that here. So I calculated H1. I'm going to do exactly the same for H2 here. Okay. I'm going to leave that part for you. So basically you have to first calculate net of H2. Let me write it this way. H2, which is equal to net of H2, which is equal to I1 multiplied by W2
Isn't it W3?
W3, yeah, that's right. Was it you, Amanda?
Yeah.
So again, you said I made a mistake? That's what you mean?
I'm sorry.
I thought over the break, you sat and thought about all what you'd done in the class before.
Not
Oh my,
really.
not really. Okay, that's fine. I1 W3. I1 W3, that's correct. Then I'm gonna have plus I2 W4. Is that right, Amanda?
Yes.
Okay, good. Plus the same B1 multiplied by 1, right? And then once you calculate this one, you're going to calculate, let's say, let me call it Y2, for example, which is equal to out of H2, which is equal to 1 plus e to the negative net of H2. That should give you, based on my calculation, a number like this, 0.596884 1920x1334. Again, you don't need that. I try to be funny here, but you can have just maybe 2 digits is enough, honestly. And calculator give it to you. I said, okay, why not? Let's use that. Good. So we have net of H1. Let me kind of put a red here. And we have out of H1, we have net of H2, and we have out of H2 so far. Now, by analogy, the next things I have to calculate here is first net of basically O1 and out of O1 and net of O2 and out of O2, right? So let's do at least one of them so I can show you how does it work. Then from there you would understand what's going on. So in order to calculate the net of O1, I don't like this. Net of O1, it's equal to W5 multiplied by out of H1. See, out of H1, we already calculated that. That was the Y, right? Plus W6 multiplied by out of H2 plus B2 multiplied by 1, right? Let's look into that. See, out of H1 multiplied by W5, okay? And out of H2 multiplied by W6 here, as you see here, W6, plus its corresponding bias, which is B2 here. Okay? Are we good?
Yes.
Everybody clear? Everybody? Okay. Now, I think easily what you can do, you can plug numbers there, very simple. You can plug its corresponding numbers here, put 0.4 multiply by the value, the funny value we found for H1, which is 0.5932 ... whatever it is, right? Plus W6 here, which is 0.45. Let me double check this W6 here. 0.45, that's correct. Multiply by out of H2, which is 0.59688 ... plus 0.6 multiplied by 1. I'm going to write this multiplied by 1 so we can remember that. I just want to check 0.6 here. Yeah, that's correct. This would give me a big number, which is 1.1. I mean, relatively big. 0.5905967. Then you would pass it to the sigmoid function. So basically your Z1, the one that we call it there, which is equal to out of O1. I'm going to pass it to 1 divided by 1 plus e to the negative net of O1, which is equal to negative 1 plus e to the negative this number, because that's the net of O1, 1.105905967. That would give us 0.75136,507. Good so far? Once again, Z1, this is the one that we in the lecture note Here I call that out of O1. How about that? Ouch. Question? Now, I'm not going to write that part, but this is exactly the same you need to calculate for out2. Do you think you can do that? I can write, actually, let's write the formula here. Let me open the picture in front of me. So I'm going to say net of O2, it's equal to, basically, I'm calculating here, right? This net of O2 here. I'm going to calculate this. This is net of O2. I'm sorry, here. Right? This is the net of O2. Okay. So, all right, let's see how I can have to open the picture here. Okay, in front of me. All right, what I have here is W7 multiplied by out of H1 plus W8 multiplied by out of H2 plus B2 multiplied by 1. Is that correct, Amanda?
I was going to say you put the negative on Z1 for some reason.
I didn't put negative on
Put a
Z1.
negative on the second fraction.
Where are you talking? Oh, here? Here? Why did I put negative here? No.
Yeah, you put a negative there. I was like, what?
Okay, no. No, it's not negative.
But
Thanks.
yeah, that looks correct, the net O2.
All right, good. Well, so Z2 here is equal to out of O2, which is equal to 1 divided by 1 plus E negative net of O2. Okay, which we calculated here. So if you calculate this one, that should give you a value of 0.7. Well, I mean, yeah, I don't have this one. I mean, I have it. I just put it the result here. You guys can calculate it yourself, the detail of that. 0.7, 729, 28465. All right, so basically our feed forward tasks is done right now. Oh boy. But yeah. Ouch. Good question. So the feed forward task is done. So once again, let's see what we have here. Well, something you need to notice here, look at our Z1 and Z2. These are the output that my network generates. 0.775 and 0.77. Clearly, you can see there is a discrepancy between that is generated and the one that we had as a label here, 0.01 and 0.99, right? So now I have to find the amount of error, and based on that amount of error, I have to build my back propagation process. Does it make sense? Okay, yeah, let's do that. Even if it doesn't make sense, I have to go forward. So
yes, it does, Professor.
So everybody okay? So I just want to make sure everybody is okay and you're on the same page. Okay, because it's just becomes sometimes just kind of confusing, but feel free to ask me if you don't understand any part of that. Okay. All right, so the next step here, I'm going to say here, calculating the total error. Oops, error. I'm going to write the total error like this. See if there is any objection. E of total equal to I try to write it even simpler so you can understand. Target minus output, sigma, for all number of outputs you have, right? So for example, target is the one that is given to you here. Target right now is 0.01 and 0.99, right? And output is the one that we just calculated here, 0.75, Z1 and Z2, for example. And when we say sigma, we have to go through each one of those outputs, right? So, excuse me. So, so for that reason, I can write this one in different way. I can say here, E of total, it's equal to the amount of error that output 1 generates plus the amount of error that output 2 generates. Does it make sense? We have two outputs, right? We generate two outputs here, output 1. This is output 2 and output 1. Each one of them, there is a discrepancy there, right? So the total error is the total error, the summation of these individual errors. All right, so for that reason, E of 0, 1, it's equal to, I'm going to write it in detail, target O1 minus out O1 to the 2, which is equal to half. Target O1, it's 0.01. So I just want to scroll up to show you here. See, this is 0.01 here. Look at that here. Minus output 1. We just calculated that, which is 0.7513 ... the rest of the digits to the 2. This one would give you 0.274811083. And by the same token, you can calculate the second error, which is E of O2 equal to half of target of O2 minus out of O2. This is equal to half of, I'm going to write it again. Well, I mean, let me kind of, to make the process faster, this is exactly the same process. You're going to basically, okay, who cares? Let me write it. Half of, what was the error here? 0.99, right? So I'm going to write it here, 0.99 minus the O2 error that we calculated here is 0.7729. 0.7729 ... to the 2, which will give you 0.02 35,60026. Good. So E of total is just total of these two. So E of total, which is my total error, is the summation of this number plus this number. That would be 0.298371109. So clearly this is not a zero error. So I have to, for example, if it is needed, I have to update my weights based on that. Are we good?
Yes.
Yep.
All right, cool. So far not bad, but wait. The hard part is going to start right now. It's not hard, it's just kind of too many steps in it. All right, so let's kind of review what we did here. If you're tired, let me know. Let me check the time. It's 6. Maybe we can have a small break here. But let me quickly review before I go to the next step. So first we construct on our network with some initialization of the weights. Then we basically created the feed forward pass with those weights. We calculated net and output for each node. We used sigmoid function on each node of hidden layer and output layer. Then we calculated the outputs, and then we calculated the total error because we had our desired output, which we call that target, and compare that with the output that is generated with the feed forward network. And then we calculated the total number of error. Since the total number of error is not 0, now it makes our network basically quite eligible for back propagation, right? For that, you could have some sort of a threshold. You can say, okay, if error is less than this much, don't do back propagation. But in this case, you probably 0.3, it's a high error. So we're going to basically do the back propagation. So I'm going to call this one back propagation, or maybe to make it easier, backward pass or back propagation, either of them. So we're going to, do you want to take a break? Because that's online, it makes you hot. All right.
I would like a break.
I do not want to break.
Okay. I have to take a break because my knee is killing me right now.
Oh, no.
I have to
That's
change
fair.
my position.
Please for a break. Thank you, Professor.
Yeah, let's take a break for, let's say, 5 minutes. It's 7 o'clock, 7:05-ish. We're gonna start again. Okay.
Mhm.
All right. Okay. All right. So everybody ready? Okay. Now, for the backward pass, basically the goal here is to calculate the amount of contribution of each one of these weights to the error, right? So based on that contribution, basically we try to either subtract or add. So that back propagation basically does that. So in other words, let's say consider one of those nodes here. I'm going to redraw it here. So consider one of these nodes. Let's say this is my out of O1 and this is net of O1, right? And this is E of O1 that we calculated, error of O1, right? And we know that error of O1 is equal to half of target of O1 minus out of O1 to the 2. This is just, we use that. And we know that E of total, it's equal to E of O1 plus E of O2. Okay. Now, E of O1 going to contributes to this. This one going to contributes to that. And then in this node, the whole node, if you consider it, weight of W5 would go here. Weight of W6 would go there. And also the bias 2 would go there, right? So just a second, let me kind of scroll up to show you which one I'm looking at right now. We're looking at this one right now. It looked like I put like a magnifier and I just look closer into that to see what happens, right? So let's put a proper label here. Also, if you review that, when you review it, you can. So this is output of hidden layer 1. This is output of hidden layer 2. And this is basically 1 because this is always is 1, right? Now, I'm trying to calculate this contribution, W5, okay? So in order to do that, if you look into that, E of total is a function of E of 0,1 and E of 0,2. E of 0,1 is a function of target 0,1 and out 0,2. Okay. Target 0,1 and out 0,1. And target 0,1 also, I'm sorry, out 0,1 also, it's it's a function of net, where net also is related to W5. So in other words, remember that derivatives that we wrote it in the lecture notes. I'm going to rewrite it here. The derivative of the error, or with respect to variable 5, I'm going to use that chain rule. If you look at it this way, so you don't have to remember that chain rule. So this way, basically, you have a better understanding. So this is the amount of differences in O1 with respect to W5, okay? Net to W5, okay, because net has dependency to W5. That's for sure. If you look at this diagram here, and multiply by out O1 with respect to net of O1, you can see that clearly they're dependent, because that's how basically, remember that out is nothing but a sigmoid function that we passed net into that, right? And finally multiply by total, E of total, with respect to out O1. Does it make sense? Does it make sense? Yes, no, sometimes?
Sometimes.
Sometimes? Yeah, let me know if you have any question. Which part of that is not basically clear? Just let me know. Let's talk, okay? So once again, we already, I mean, all of this formula is already known. I think this is not something new. I think you understood the feed forward. In the previous step, I showed you how each one of these components get calculated. So for example, net of O1, which is here, it's a function of W5. That's obvious, because the linear combination of W5 with output H1 here and W6, H2, and B2 and 1 would make net1. Then I pass net1 to a sigmoid function here to calculate this out of O1, right? This is the sigmoid function. Then this out of O1 basically, targets minus out of O1, basically that gives me the amount of error that I would see in this output, right? Now I'm trying to find out the amount of differences that I need to make on W5 for the gradient descent, right? That amount of differences, because remember the gradient descent formula was like this. For example, W5, it's equal in stage K, it's W5 in stage K minus 1 plus eta or alpha, whatever you call that, alpha, for example, that learning rate of and the derivative of basically a whole this derivative, right? So you have to come up with some sort of function derivative of error with respect of W5. Directly, I cannot calculate it. I calculate that, but I know that all these dependencies here, I know that net of 0, 1 has dependency to W5. Net of 0, 1, it has dependency to W5. That is clear. That's how I calculate net of 0, 1. Output has dependency to net O1. That's clear, because output is calculated by using the sigmoid function when I pass net of O1 to that. And total has dependency to output. Yes, because E of total is equal to E of O1 plus E of O2. Okay? Clear?
Yes.
All right. Now, knowing these things, the rest of that is just pretty much basically, again, playing with these numbers here, right? So we have this formula right now. Let's kind of look into that. I'm gonna write first E of total in order to calculate it. I'm gonna write E of total. I'm gonna expand it. So I'm gonna write it down one more time here in order to make it easier for the derivative, because as you see here, I have a derivative here in this part. So E of total is equal to half multiplied by target O1 minus out of O1 to the 2 plus half target O2 minus out of O2 to the 2. Okay. Now, the derivative of E total with respect to out 1, because that's what I'm going to calculate here, I need that, is equal to, it's basically, it's minus target O1 minus out O1, right? Why? Because my variable is O1, right? Since variable is O1, so this whole thing becomes 0. Here basically become, this 2 goes there, 2 divided by 2 become 1, and I have 1 minus out 1, which makes me that negative here, and the entire statements here, target O1 minus O1. This is just a typical derivative. You can, if that confuses you, you can just put out of O1 like X, and then try that derivative. Now, if I just replace the numbers, because all of those numbers is already calculated for me, negative 0, 1, 0, 1. So this is target of O1 minus 7513 dot dot dot. This numbers is already calculated. So this would give me 0.74 13 dot dot dot. Good. All right. Now I'm going to continue that. The rest of them is just pretty straightforward, because basically what I need to do right now, I'm going to calculate this derivative. Let me put it in red here, this one. The derivative of out O1 with respect of net, and then finally the last one. So let me write that quickly. So we know that the out of O1, it's equal to 1 plus E of minus net O1. We already seen that. I have it here. If you don't believe me, we already used that here. I mean, this is out 2. For out 1 is exactly the same here. Okay, so this is not something new. We already seen it in the previous steps. Now the derivative of, I mean, O1 with respect to net of O1 would give you, this is the derivative of basically this function. I mean, this is pretty standard. Out O1, 1 minus out of O1. This is the derivative. It's not something that you can memorize it. This is, so basically any function f of x is equal to 1 divided by 1 plus e to the negative x. The f prime of that with respect to x is equal to x 1 minus x. That's the derivative of that. So you're going to plug this number, because out of 0, 1 is already known. If you plug them, the number you get here, 0.11868 dot dot dot. Well, let me write it down here. Actually, this is not dot dot dot. I have to write it one time. So this is equal to 1.0186815.602. And finally, the third part of that is this one, which is the net. First, let's write the net of O1. Then we're going to calculate the derivative. That is so easy to do that. I'm going to write it quickly here. If you don't mind, I'm going to erase this. For the last part of that is net of O1. It's equal to W5 multiplied by out of H1 plus W6 multiplied by out of H2 plus B2 multiplied by 1. I just dropped the 1. And the derivative of net of O1 with respect to W5, it's equal to out of H1, which is equal to 0.59, which we already have that value, 32 dot dot dot. Good. Now we have all these three components. We have this one, the first one, we have this one, and we have this one. Now, in order to find the differences, easily I have to multiply all those values. I'm going to put it here for a second. So you guys, if you want to take a note, you can take it. But just for fun, I'm going to write it one more time. The derivative of E of total with respect to W5, it's equal to E of total with respect to out of O1 multiplied by O1 multiplied by out of O1 with respect to net of O1 multiplied by net of O1. This is the chain rule. So this way, basically, you would understand where that chain come from. So all you need to do, you would say here E of total, it's with respect to W5, it's equal to multiplication of each one of them. I'm not going to write it again, but that would give you 0.082167004. Good. So you can see right now how much work involved in that. So this is just for one weights, just W5. For this small network, we have to repeat that for W6, W7, and W8. I'm not going to repeat it. I'm just going to write the end result for that. Makes sense so far?
Yes.
Yeah,
I
I think
know
so.
you may need some kind of work on that, but again, I'm not going to give you like this deep of question for sure, but expect to basically, for example, being able to write portion of that, a small portion of it. Okay, and if you look at the homework, you would get basically the idea. I would give you more questions on this. Okay, this is probably is the comprehensive question. You know, it just covers every part of that. All right, now I have W5, the derivative. Now I can use the gradient descent to calculate the amount of the new amount of W5. So the new W5, I'm going to call this one, I mean, technically in the lecture notes, we have K or K plus 1. Since this is the, I can put 1 here, but let me put it plus here. So that shows a new or updated value of W5 after applying gradient descent, GD. Okay? So this is pretty easy. The new W is equal to the previous W, which is W5, minus, if you want to call it eta or alpha, it doesn't matter. So this is eta, which is the learning rate, multiplied by the E of total with respect to W5, which we already found it. So W5, the previous value for that was 0.4 minus, I'm going to consider eta, again, that's a constant. I'm going to consider it equal to 0.5. This is probably, it's given to you, or you can choose that. Multiply by this value that you just found it here. Right? This would give you 0.3589168. Let's see what happened. From 0.4, the weight reduced to 0.3. Okay. Of course, neural network's task is to calculate all this, the same steps for W6, for W7, and for W8 in order to make the network ready to calculate the W's from hidden layer to the input layer. But I'm not going to calculate it. I'm just going to write the end result for each one of them for W6, W7, and W8. I'm going to give you some time to think about it a little bit, then
Professor, I have a question.
Go ahead.
So we're updating the weights for after the first after H1 and H2. Will we be updating the weights for like W1 through 4?
No, that's the and see, do you remember when we did that one, when I showed you the lecture notes, I had two derivative sets, one of them from output to hidden layer, the other one from hidden layer to output layer to input layer, right? So now basically I'm just calculating from output layer to hidden layer. That would cover, so this method that I showed you, that would cover W1, W5, W6, W7, and W8. Then after that, I'm going to show you how you can do see, right now, we just calculated W5, W7, 6, and 8 would be exactly the same, right? Then I'm going to show you how you can do W1, W2, W3, and 4. Okay. All right, just give me a sec. Actually, that one requires a little bit more work, but I think at least one of them, I'm going to show it to you, but it's pretty extensive, but I think it's worth it to show you one time at least, so you have an idea what's going on there. So by the same token, W6 will be, if you do the same calculation, would give you 0.4 0.086666186. W7 would give you 0.511301270. W8 plus would give you 0.613702121. Okay, so we have all this W's. Now, the big one is just to start at hidden layer. Before I start the hidden layer, I'm going to draw it exactly the same as I did like a big one. Let me kind of explain that. Then I'm going to basically start calculation. Are we good so far, up to date? Do you need any question? Do you have any question? All right, so let me write here the hidden layer. So the previous one, when I started, did I call? Yeah, back. So this is for output layer. The other one I'm going to call this hidden layer. Okay. Now, once again, I would like to kind of have something like this. I want to draw it like bigger. Same network, but let me draw this one with a different color here. This one, and perhaps this one. Then I'm going to have here and here. And here I have E of 0,1. Here we had E of 0,2, right? So what we did basically, we used in the first step, right? We calculated this. Make sense? Of course, this one I showed you in detail, but I did exactly the same for this node as well. But I just wrote the end result. So basically, I calculated W 5, 6, 7, and 8, right? Now, here I have out and I have net, right? So now what I need to do is, so we have this part. Now I have this part. I have to calculate W1, right? Let's see, how can I write the formulation by knowing this thing? So you can see, in order to do the E of total with respect to W1, that's what I'm trying to do right now. There are several dependencies are there in between. All this red back arrows shows the dependencies. Let me write it down. It would basically clear it out probably for you. So first, let me write the formula that we already know that, which is E of course, in this diagram, I didn't draw the bias, but this bias also is the same as we had before. E of total equal to E of 0, 1 plus E of 0, 2, right? Something that I'm trying to find out here is the derivative of E of total with respect to E of W1. So basically, I would like to see how much I need to change W1. I need to use this, the result of this derivative into my gradient descent. Okay, so based on this diagram, this is equal to the derivative of E of total with respect to E of out H1, which is this guy. This is H1, and this is H2, multiply by derivative of out H1 with respect to net of H1, multiply by net of H1 with respect to W1. Make sense? Again, chain rule. This chain rule become a little bit larger because E of total with respect to out of H1 also can be extended. Because E of total with respect to E of H1 will be like this. It's E of total with respect to E of, I use this formula O1. I use this formula Bez plus okay. Now let's start working on this. It has a little bit more steps into that. It's very similar to what we did previously, but a little bit more steps into this. I'm going to do at least one of them for W1, and then I'm going to give you the total result for that. That basically sets you up for the entire network for the back propagation. So it tells you basically what updates we need to do. All right, let me start here. Let me start from E of total with respect to H1. I'm going to start from this one here, this time. Good? Any questions so far? So basically, my task right now is to calculate each one of these terms, right? Then multiply them. When I multiply them, then I find this one. Then I'm going to use this term into the gradient descent to find the amount to, this basically gives me the amount of changes I need to make. Then I use the gradient descent by, subtracting from the previous value of W1. That would give me the updated W1. This is the whole steps. This is pretty, again, a little bit cumbersome. Otherwise, it's not that hard to do that. So I'm going to do this. So we know that E of total here, we know this formula. I'm going to write here E, the derivative of O1. This is a little bit probably H1. See, E1 with respect to H1. This one we already did it on top. It's equal to net of O1 multiplied by, see, I'm just doing this one right now. Okay. Okay. Once again, in order to convince yourself, see E1, E of O1 net of O1, E of O1 net of O1 here. See, this is E of O1 is the amount of error I have. So with respect to net of O1 out of O1. See, this is net and out. So these are related to each other, and outs also to E of O1. All right, so this is probably the hard part. Again, there is another chain rule you have to use. This is exactly the same as what I had in the notes, basically. So I'm going to replace that. So these are already, we calculated that. If you go back and look at the up calculation, E of O1, net of O1 is already calculated, 74, 41, ... multiply by net of O1 out of an sorry, one little mistake here. Okay, no, this is good. I think the numbers were okay. Now this requires another chain rule, because directly E of O1 and net of O1 is not related. I have to see E and net directly is not. There is a out here in between them, right? Look at here. So net and E of O1, there is an out here. So I'm going to make it like this. E of 0, 1, net of O1, it's equal to O1 out of O1 multiplied by. So these are, we already calculate them. It's not new in terms of the O1. So basically, this is out with respect to net. This is E with respect to out. We already calculated all of them. So I'm going to put the numbers here. 7413 ... multiply by 0186 ... This one would give me 011384 98562. Okay, so I calculated this part. The net of O1 with respect to H1, it's easy. Net of O1 with respect to out of H1, which is equal to, because we know that net of O1, I'm going to write it here, net of O1, it's equal to W5 out H1. So again, it's pretty trivial here. 6 out of H6, 2, sorry, plus B2. So if you take a derivative, that would directly give you W5, which is equal to 0.04. Okay. Now I have both of these terms. I can calculate net of E1, which is this guy. I can say E of O1 divided by, sorry, out H1 equal to 0.1384 98, the rest, multiply by 0.4, that would give me 0.05 5399 425. Okay, so we calculated this part. Which is here. Now we have to calculate E of 0,2 with respect to out of H1. I'm going to leave it here. It's exactly the same process for the second one, which is E of O2 with respect to out of H1, which is equal to negative 0.01, 9049119. Okay, now I have both of these terms. I have this one and I have this one. I can calculate the total here, right? So I'm going to write it here. The amount of E of total with respect to out H1. It's equal to the summation of those two, which I already have. I'm going to just write the numbers here. 0, 55, 39, 9425 plus, or minus here, minus 0.019, the rest, which would give you 0.03635036. All right. So again, the second one is it requires more process there, but there are a few more process left for that. I think not too much left. Let me go through that one time, then I think that's good. Now we have this one. We have this total here. We need to calculate this one and this one. Once so this term is done. These two is remaining. Once I have these two, then I have to multiply them in order to find the difference for the W1, right? So I'm going to figure out right now the out H1 with respect to out, I'm sorry, net H1. So once again, comes from here. Out H1 here, net of H1. This is, in fact, is not that hard to do that, because out of H1, it's, because that's an out, right, is a sigmoid function. It's pretty easy. Out of H1, it's equal to 1 divided e to the negative net of H1. This is pretty easy to do that. So this one, basically, in terms of the derivative, so this is the out, would give you out of H1, 1 minus out of H1. Once again, if you plug the numbers, we already have those values. It would give you 0.241300709. Okay, so that's easy to do that. And the last one here, if you go back here, which is net of H1 with respect to W1, which is the last one here. This is also fairly easy to do that. Net of H1 with respect to W1, right? So net of H1, it's a net, right? It's a linear combination. It's W1 multiplied by I1 plus W3 multiplied by I2 plus B1. So this derivative would give you I1, which is equal to 0.05. Now we have all three components. I can calculate the amount of error of total when W1 is variable, but basically by the multiplication of these three values that I already calculated. 0.0363536 multiplied by 0.2, which is here, 13 ... multiplied by 0.05, right? If you calculate this one, would give you it's a small number, 0.0043858. All right, I have this one. Now I'm going to write an update condition. Update condition for W1. Let me write that part, then I can pause a little bit. Then let me know if you need me to scroll it up and down. So W1 plus, so this is exactly the same. So this is a updated value of W1 by gradient descent, which will equal to previous value of W1 minus eta, or alpha if you want to call that. This is the E of total with respect to W1, which we already calculated here. Just we plug the numbers there, 0.15 previous value minus Eta, I just keep it 0.5, multiply that, this is small number that I have it, 0.0004 ... which will give you 0.149780716. So you can see here the amount of W basically is just updated about 0.01. It's very small, but it's still an update. Okay. We have to repeat that for W2, W3, and W4. So once I finish that, then I have all my W's ready for forward pass again. Make sense? Sorry, it was a lot of steps into that, but I really, again, I don't think that are easy, hard, but probably you need to one time you just read it, go from beginning to the end, and everything just clicks off. Otherwise, it's just pretty easy to do. Very easy. It's very mechanical, basically. All right, I pause that here. If you want to take a note, do that. Then I'm going to write the final answer for W2, W3, and W4, and then technically we're done. Then I'm going to kind of quickly review it one more time. Then we can stop it there. If you have any question, let me know. So W2 plus is equal to 0.19956143. W3 plus, it's equal to 0.249751114. And W4 plus, it's equal to 0.29950,229. So all these pluses that I calculated here, 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 and here, and also for W5, 6, 7, 8 are the updated ones. Okay. Make sense? This is the ultimate neural network. Basically, we did everything manually here. Okay. So if you look at the homework is much, much smaller than this, okay? I'm not going to give you these questions doing them from beginning to the end, but what I expect, I don't even care what do you want to call that. If I give you, let's say this, something like this, for example, right? And I ask you, for example, just this question, what is your formulation to update W1? Just a formulation, for example, you should be able to write that. Okay, that's as simple as that. Or if I ask you, what is the out H1 here? You should be able to write it. Okay. Or I give you some numbers and for example, all those numbers, then I ask you, okay, calculate W1 plus, for example, right? I'm not going to ask you to do everything from scratch. All I'm saying here is what I would like for you to understand all these relationships here. That's all I want. Okay. So always, most of the time, we're going to use this function, but be ready if I just change this function to something else, you have to just take a derivative. Really doesn't matter for you in terms of the calculation. Whatever function I give it to you, you have to be able to make a derivative. That's all. Right? It doesn't matter what function is this activation function. Make sense?
Yes.
All right. So go through it one more time, and then so next, and also go through the homework. And so next time, of course, there are a few slides left. I'm not going to continue that today. I think it's too much of things here. So next session, I'm going to finish that, and maybe I can do some more exercise on that. So make you ready basically for the test. And yeah, so since our test will be next Thursday, once again, I'm going to say that it's on 18th, not 16th. So next session lab, we're going to allocate a little bit of review of the materials, and also, of course, starting our neural network lab. One neural network lab at least. We're going to have that. Okay. Any question?
Yeah, I have a question.
Okay, go ahead, please. Yeah.
Regarding like updating weights. So it
Uh-huh.
seems if we're searching for the ideal weights to guarantee like the highest possible like accuracy of this neural network, we're not necessarily we're going to be focusing on updating the weights in from the hidden layer to output layer, correct?
If what was your question again? Did you say, okay, what is the best weight update? Is that
Yeah,
your
especially because because as I was looking at the
right?
weights from the hidden from the input to the
Right.
hidden layer, it looks
Right.
like we didn't really update them that much. But in
Yeah,
contrast,
yeah. Okay, so these are several things. So first of all, there is no best. Okay, so remember, I just did one iteration. So please pay attention to that. I did just one iteration, back iteration, and forward for 1 point, right? So imagine, do you remember those epochs and all those things? All this process would be keep repeating, repeated. So that's one thing. Second is the amount of update, the amount of walking here, it's really, so that's the same concept as gradient descent would apply here. For example, if you would like, well, I mean, that depends on depends on the value of the back propagation. For example, what value of changing basically this one produce for this node, and therefore this one needs to propagate for W1, because when I calculate W1, clearly there is a dependency to this value and this values as well, and also the dependency to the errors as well. So that depends on that, and also depends to the learning rate as well. So these are the parameters basically we change that. But saying that, okay, it just changed a little bit, yes, that's sometimes it happens like that. So basically network believe that much of changes, it's enough. So I mean, unfortunately I don't have, if someone curious, I'm maybe tonight, or someone if it's curious enough, if you feed forward this network to see what you get, maybe I have those results here. Let me see. So the previous error was 0.2983711009. Okay, so this is the original error I got, right? Now, if I basically feed that network with the new weights, I'm curious to see what is the new error for that. If someone can do it, that would be great. So basically take all these plus weights and then do this step of feed forward again, and then calculate the E of total to see what error you get new one. So I'm guessing, or at least I'm hoping, that our error becomes smaller in the next round. Make sense? That's what I'm saying. So in other words, basically really being small changes or big changes, we don't have that much of control on it. We don't know it that much. That's why a neural network usually is known as a black box. Why black box? Because mathematically, really, I cannot tell you why this one went. I mean, I can tell you probably because of network basically itself kind of finds out how much contribution it needs to basically add to one weight or deduct it from one weight in order to make the next round closer to the result. That's what I'm saying here. So yes, contribution, if it's small, that's okay. I mean, as long as if you feed forward it again and it shows a update to the weight, so that means less error, that's a good contribution. That's what I'm saying here. But there are, of course, some rules. For example, when you initial the weights, usually, again, this is totally arbitrary. I gave it to that, or at least I gave this arbitrary number such that I have a good result. But for example, we never put like a large number here as a weights here. And usually our biases are very small as well, right? Usually we try to avoid put numbers really close to zero, right? For example, 0.01 or something like that, because that creates another bias. And there is also a possibility that when you do several rounds, you don't see any update, right? Basically, you might get stuck in one of those local minimum there. It's not a global minimum because of the back propagation. Okay. There are some more technicality, a little bit left. I think I have to show it to you a little bit more about the classification part of that, which I think I talked about that, about the output of the Z basically is 0, 1, 0, 0, and something like this. But I'm going to talk about that next time. Any questions?
I have one more. Oh,
Go ahead.
So when we're up, will the neural network update all the weights or just one way at a time? And then calculate.
When you say all the way, you mean the weights?
Yeah, all the weights.
Yeah, no, weights is all the way. So basically, when it does the back propagation, all weights get updates. Now, what I'm saying is neural network should find that the amount of contribution, because see, this is what we expect, right? What we got here as an error. Do I have the values here out of E of total? Just a second. Let me find out E of total here, right? The amount of error here is E of total E 0.29, 0.29, right? The amount of error I got here is 0.29. This is total. And I have the error for each one of them. Now the neural network should actually, let me write each error also as well, E1 and E2. Let's remember that. So that is basically out 1 and out 2, right? So out 1 is 0.7 and 0.75, 0.77, right? Okay, let's write it here. 0.71 and this is 0.77. So you can see here, this is a huge difference, right, between these two. Whereas this one is much less than that. So this network should kind of understand that the contribution of probably W5 and W6 probably should be larger compared to W7 and W8. Make sense? So that's the reason what I'm saying is network has that awareness. Basically, it does that by the back propagation. And again, the result may not be successful because of the local minimum and that sort of issue, or overfeeding, but the iteration would kind of make it guarantee that it does it over and over, and finally I reach that, as long as I'm not into the local minimum there. Okay, make sense?
Yeah, that makes sense. Thank you.
Okay, all right. I think someone else had a question too. No one question? No question? Are we good? All right. So I'm going to stop here. The video takes time to be rendered. Then I'm gonna post you the link. So you can have it as a reference in case if any part of that you have kind of doubts, you can just kind of fast forward it. I don't think we can just sit down and watch it again. But again, you can fast forward to places you want. Then prepare for the next session, then we go forward on that. So far, I think next session also is approved to be like online. In case, if hopefully, who knows, maybe if I get better, I would rather to turn it to the regular classes. I let you all know. I'm gonna update you on that. Okay.
Okay.
All right then. If you don't have any question, I'm gonna stop here, and I see you all next time.
Thanks, Professor.
All right. Thank you all.
Thank you,
Sure.
Professor. I do have a personal question.
Okay.
How did you mess up your knee?
Oh, I think I said that. I mentioned that. I just fall from slope on skiing.
Oh,
Yeah.
I'm sorry to hear that.
Yeah, that was pretty embarrassing, right? So I've been doing that for a long time, but I really mad at myself, because of that.
Yeah,
I think I mentioned that to you one time. I was like, oh,